It's our pleasure to have David Anthoff, who's an environmental economist, talking to us. I think one of the things that's interesting as well that I learned as we were setting this up is that besides a lot of the work in environmental economics and social cost of carbon that you're going to hear about, he's also been a core contributor to the Julia programming language, which I think MIT has been kind of a center of mass for that for a little while, but maybe you've been pulling that center of mass farther west. So anyway, it's a pleasure. Thanks.
All right, thank you. Yeah, it's great to be here. Always like to be here. I think Julia is sort of my normal hook to come to MIT, but it's great to talk about my real research here as well. Okay, so I'm going to talk about the social cost of carbon. The talk really it's sort of a very broad overview talk. That's the goal, and I will try to weave in some Julia at the end, because when I come to MIT, I just have to talk about Julia. There's no way around that. So just to give you sort of what's the context of all of this here. Social cost of carbon is an estimate in dollars of the economic harm that you cause if you emit a ton of CO2 into the atmosphere. Okay, that's what the social cost of carbon is. I had to update that slide a little bit. The SEC was widely used in the federal government for regulatory impact assessment of any policy that might have changed emissions. And it was, and I'll talk more about that. That has changed under the current administration. So right now it is not being used at the federal level. But there's still lots of other countries, states, private sector where it still plays an important role, but that's sort of where we are right now. And so what I want to do today is I have three parts here in my talk. I want to talk about, I will introduce the social cost of carbon, how we compute it. Then I will talk about how it is used in policy and a bit about the history of that. That's the first part. The second part is I will talk about a large-scale project that I co-led with a friend that produced a new SEC estimate for the federal government. And then at the end, my Julia part, we built a lot of computational tools, and it's quite interesting to see how they enabled a close collaboration with policymakers, and I'll talk a little bit about that. All right, so this is the outline. I also have a fourth topic. There's no way on earth that I will get to any of this, so just ignore that. So let's talk about what is the social cost of carbon. I already gave you sort of the colloquial definition here. If you are an economist, this is maybe a more precise definition. It's the expected net present value of marginal damages from CO2 emissions. And I will now just walk you through a very simple picture of how we actually compute it. Okay? So we start out by taking two emission runs over time, two global CO2 emission runs over time for CO2 emissions. And we call one the base run. And it wouldn't look like a straight line in real world. It would be a projection of CO2 from the IPCC or something like that. And then we modify this emissions path a tiny little bit in that we add one extra ton of CO2 emission in the present. Okay? And then we take those two emission paths and run both through climate models. And this is actually what I have here. So we take both paths, we run them through atmospheric chemistry models to trace out what that implies for CO2 concentrations over time. And you can already see this one little blip in the beginning, of course, has, because CO2 concentrations are a stock, will have an effect in the atmosphere on the stocks of CO2 for centuries. We trace that through what it means for temperature. And then we trace that through what that means for economic harms in different parts of the world. And we're really interested in this delta between this base run and this marginal run, because we want to understand what this initial blip here, what that caused down the road. And we use certain types of models to do all of this. And then at the end of that, we get a table that looks a little bit like this, where we have for each year and in each country or region in our model an estimate of what the incremental extra harm is that was caused by that one extra ton of CO2 emission. And just to give you a bit of a preview, when I say economic harm, I'm talking about things like how much did this cost us in terms of agricultural productivity? How many people were their health had affected by this incremental CO2 emission? Did we have to build new seawalls to protect against sea level rise and things like that, okay? And then we have this table, and you might think, oh, now it's easy. We just add everything together, and then we have our total damages. And you would be mistaken, because climate economists for about 40 years have probably spent most effort and time fighting about how to add everything up, okay? And so broadly, the story here is that we do add things up. These are these little cells here, but we weight them before we add them up. And that's the literature on discounting in climate change. And the question is, how much less weight do we give to harms that occur in the future? And they're not going to go into that debate in detail, but the determination of what exactly we use as our discounting factors here has been a major, major topic in climate economics for a long time. And then, of course, we do everything probabilistic. So we run Monte Carlo simulations of all of this. So we don't actually get individual numbers. We get probability distributions for all of that. And we really get an expected social cost of carbon at the end of our exercise. Okay? So that's how we compute it. The type of model that you use to compute these kinds of estimates are called integrated assessment models. At MIT, you have some very well-known, very large integrated assessment models. The integrated assessment models that are used for this kind of exercise tend to be simpler than these large-scale energy integrated assessment models, but they still combine different parts. You know, they have a component for the economy, for chemistry, the climate science itself, impacts. You know, we try to estimate the harms in different sectors of the economy. There's a component for population. So all of these things are inside these integrated assessment models, and then you run those to come up with this table that I showed you. All right, so now you've estimated a social cost of carbon. What can you do with it? Why is that a useful exercise? And I'll just give you a few pointers for what this has been used. So one, in sort of an economic theoretical framework, it tells you what the optimal tax on greenhouse gas emissions should be. So in an optimal tax framework, you can use the SEC as your tax rate that you charge per ton of CO2, and then everything will be great. Okay, so if you want to set a carbon tax, SEC is the metric by which you set the level of it. If you have a cap and trade system somewhere, like for example the European Union or the California cap and trade system for greenhouse gas emissions, you can use the SEC to evaluate whether your cap is too stringent or too loose. So if the carbon price in that permit market is way below your social cost of carbon, your permit market is probably not stringent enough. And then the primary use case actually for it is it makes cost-benefit analysis of regulatory actions really, really simple. So if you have a regulation at the federal level that changes fuel efficiency of cars, and you come up with an estimate of what that does to your emissions, you simply multiply that change in emissions with your unit value for emissions in terms of economic impacts, and you have the welfare impact of that change in emissions. So that's been the most prominent policy use case for the social cost of carbon, that all federal regulatory impact analysis of all regulations at the federal level use the social cost of carbon to quantify the benefits of reductions in emissions. And that's really where this SEC had a major, major role, because it was the primary way in which all of climate science and all of this information flowed into the regulatory process. So it's almost like a gatekeeping tool for a huge amount of science that is being done in the background. And then finally, there's just, from a purely academic point of view, lots of interesting things that you can do around the social cost of carbon. You can ask how it changes if you care about equity. You can do game theory about coalition formation, and there's an endless list of applications that you can do with it. All right, so that's sort of a little bit of what it is. Next, I wanted to talk a little bit about the policy history of how and when it was used and then not used, to give you a sense of what impact it has had. So you will find a lot of US economists running around telling you that the SEC was first used under the Obama administration for policy analysis. And that's not true. The first use case was actually in the United Kingdom in the early 2000s, I did a master's degree back then, and that's sort of how I was dragged into all of this. The United Kingdom used it for regulatory cost-benefit analysis of individual projects and regulations. There were lots of problems around how they did that. There's a lot of inconsistencies, but it was a use of the social cost of carbon in their framework. The UK coincidentally gave up on using the social cost of carbon concept entirely just when the United States started to adopt it. And the reason was that the United States moved to a framework where they picked a climate target independent of economic analysis, and then used economics to figure out what the least cost way is to achieve that climate target. And that gives you a marginal abatement cost estimate. And that is also a carbon price. And then they use that framework entirely for their work and have not adopted anything SEC ever since. Germany, where I'm coming from, actually started using it SEC in 2007. It doesn't play a big role in Germany. Germany does not have a long tradition of cost-benefit analysis, but there is one on the books. There's a funny anecdote that I could tell over dinner or something like that about how that came about, but that is sort of another application. And then really probably the most impactful one was the United States. Under the Obama administration, they adopted an official social cost of carbon for the United States. It was an interagency working group between the White House, EPA, DOE, and lots of other agencies that came together and decided on this is the official SEC for all the federal government, and then it was used up until last year for all like dozens and dozens of regulations used it to in their regulatory impact assessment. There's some private sector use as well. Some accounting firms used it at some point. Some universities used the social cost of carbon for their internal carbon pricing. We've worked with the UC system, for example, on that. So it's been used pretty widely. Here's an example of a use case at the federal level. This was the Clean Power Plan rule that the Obama administration proposed. It never made it out of the proposal stage. It got hung up in litigation that ended up in front of the Supreme Court, and then events overtook it. But this is sort of an example how it might be used, right? So you can sort of ignore the different options. They are small variations about the policy. But for a given policy, you have the cost estimate. That's the mitigation costs. Then you have an estimate of the local health benefits. So that is sort of air pollution goes down if you shut down coal plants. So this is not related to the social cost of carbon. And then here, you have estimates of the climate benefits of this regulation. And they split it out for different discount rates. So they presented the results for different choices of this weighting that I talked about. But this one was sort of the central one. And you can see, the climate benefits of that rule would have outweighed the costs of the rule by itself. The proper way is to actually add the climate benefits and the local air benefits together. And then they would really have dwarfed any cost. But that's sort of the kind of exercise that policymakers do with this. Ever since the United States federal SEC was adopted, it had sort of an effect that the concept percolated sort of through into lots of other spaces. So obviously, the primary use case was this regulatory impact analysis. But then it started to be used in court cases. There was, for example, a famous court case where, I don't remember the details, but someone sued the United States government and said, you're clearly causing harm. The federal government said, oh, we don't know that. And then someone said, but wait a second, you have a social cost of carbon where you yourself are saying that CO2 emissions are causing harm. So it showed up in court cases like that. Other countries started to adopt it. Canada and Mexico often follow the United States lead for regulatory analysis. A lot of states adopted it. I think this list is actually outdated. There are many more states that currently use social cost of carbon in some form for their policymaking. And then it also had sort of an intellectual impact. This was a piece like probably a decade ago or something like that, written by sort of very prominent, I would say, conservative thought leaders in maybe a previous generation Republican Party that argued for a carbon tax, essentially. And lo and behold, the level that they argued for was exactly the social cost of carbon. So it had sort of this intellectual influence that people rallied around that number as this is really what the price on carbon should be. All right, let me talk a little bit about the current situation because I'm sure people are interested what's happening right now. And I'll start with the first Trump administration because we've been through this once before. And that was quite interesting. So they left the entire social cost of carbon framework in place. So they did not start to question the natural sciences. They didn't say we don't want to do regulatory analysis, none of that. Everything stayed in place. They kept using the same models to estimate the social cost of carbons, but they changed the numbers, okay? And they changed the numbers in two ways. So one is that they used a higher discount rate. That's this weighting factor that I showed you. They jacked that up, the discount rate, which has the effect that the number gets smaller, okay? So that was number one. And then they only counted domestic damages, okay? So normally when we compute a social cost of carbon, if I emit a ton of CO2 into the atmosphere, the harmful effects of that are felt across the globe. And we add all of those harmful effects up. And the Trump administration, one, changed the computation so that only the damages within the United States were counted. Those small two changes got them a social cost of carbon of $1 per ton of CO2. And just to calibrate it, the Obama administration number was about $50. Okay, this was an effective way to de facto not have a social cost of carbon, right? And I think it was always interesting. So the discount rate of 7% is ridiculous. That makes no sense. There's no academic support for a choice like that. But there was guidance on the books in the federal government that supported that kind of discount rate. And the domestic damages only question is really tricky. It's sort of unclear whether that's, So I think at some level, this was someone knew what they were doing. Because, yeah. OK, so second Trump administration, very different strategy. OK, so in practice, the SEC concept has been dead right from the beginning when they started. So there was an executive order, I think on day one or something like that, just rescinding all the SEC estimates and saying it shall not be used anymore unless it is required by statute, and it is not required by statute. So that killed it. But now the situation is is very different because the current Trump administration is trying to rescind the endangerment finding. That's sort of a long legal story, but essentially if that succeeds, then EPA is essentially saying we think we actually don't have any authority to regulate any greenhouse gases at all. And if you don't even have authority to do that, you don't need to quantify anything because it's not a problem that you're in charge of. All of this is going to end up in front of courts, and I am not a lawyer, so I will not make any prediction how any of this will work out. OK, so that's a little bit. Let me just say one thing, because all of this always ends up in court. It's a very different environment to work in, because everything you do, you have to, in the back of your mind, you have to know, OK, I cannot take any shortcut. I cannot do everything will be scrutinized to a degree that I think is quite unusual for academic work normally. All right, second part of my talk. I want to tell you a little bit about a major effort to estimate a new social cost of carbon for the federal government. There were different phases in the federal government's social cost of carbon exercise. When the federal government initially started this, they used existing models that were pretty old, 3 models. One of them I co-maintained at that time. And that was a great choice back then. But there was also a recognition that we actually really should try to do latest science, greatest and best things. And at the end of the Obama administration, we put together, for economists, certainly a large team of people trying to come up with a new estimate that then a future administration could use. Okay, and I'm going to talk a little bit about that effort. So this all came out. This is sort of the end result of that. That is sort of our main paper, where we present this new social cost of carbon, and then that was the number that the Biden administration adopted for the federal government. I just want to highlight one thing here already. Traditionally, the social cost of carbon was created by very small teams. My supervisor and I were the largest team in the previous era, and we were a team of 2 people. And we did everything. We did the demographics, the atmospheric science, the economic growth, the damage functions. It was crazy, okay? And so one goal with this effort was I really wanted to bring together domain experts that know the best demographer, the best person for economic growth, the best person on each kind of damage function. And so this is the team that we assembled to do this. And that is very unusual in the economics literature. Normally, econ papers are written by 2 or 3 people. Okay, and I think this is 25, if my or something around that. That cannot be actually, but so roughly, roughly on that order. And we also worked really closely with EPA technical staff because we wanted them to be involved in this effort from the get-go. All right. So what was the primary output from this initiative? We built a new integrated assessment model that you can use to estimate the social cost of carbon. We built a computational platform to build integrated assessment models, and that's my third part. I'll talk a little bit about that. We created new socioeconomic projections, probabilistic projections of population growth, economic growth, and emissions for a very long time horizon. We adopted modern climate science components because the previous generation of these models really used outdated stuff. And then we introduced a discounting approach into this policy application space that is more consistent and hadn't been used before. Very brief preview of what we found at the end, right? So everything was new. I think another novelty here was that we tried to really represent all the uncertainties in this system. We tried to, when in doubt, put on a probability distribution on a parameter and make sure the uncertainty propagates through so that we don't present an overconfident result at the end. And the final number we got was $185 per ton of CO2. And that compares to the $51 per ton of CO2 in the previous iteration. So this was a big change from the Obama to the Biden administration number. And that, of course, justifies more stringent climate policy. And then that became the official federal SEC. GIVE is a modular framework for calculating the social cost of carbon. So it has all these different components that I sort of hinted in this other figure at already. So we have something about population, income, and emissions. We have various components that compute temperature, sea level rise, ocean acidification out of these. I'll take your question in a second. And then we have various damage functions that translate that into monetary damages. And then at the end, we discount these things. So that's sort of the structure of GIVE. And different parts of the team worked on different parts of these components. And I had one question here. Yes? Yeah. Yeah, I'll get to that later. When I'll have a whole section about the results. Yeah. OK. So I will rush through each of these components now, but just give you a sense of what we did. OK. There are lots of slides in here that I will skip because then otherwise I stand no chance. So the first one were these RFF socioeconomic projections. They are multi-century probabilistic projections of country-level population and GDP, and then global GHG emissions. Traditionally, in the climate literature, people use what we call scenarios. And you can really think of these as one state of the world, consistent stories about the same variables, but there are no probabilities attached. Okay? So a given scenario is supposed to be plausible, so it shouldn't be something where you sort of say, oh my god, this makes no sense at all. But the people that create these scenarios are very careful to make statements along the lines of, we are not telling you which one is more likely than the other one. They're plausible and they're used to explore the futures. And that's very useful for some contexts, but if you want to compute an expected social cost of carbon, that doesn't help you. And in the past, what has happened is that policymakers take different scenarios, assume each one is equally likely, and take an expectation. And that's a really unsatisfying state of affairs, because that's not what the creators of these scenarios ever had in mind. So we really wanted to create probabilistic scenarios that are made for this task. Okay? We wanted to account for correlations between these different time series, so that's a sort of part of this. And then we used different methods, both statistical and expert judgments, to come up with these scenarios. All right, I'll just tell you roughly what we did for each one. So for population, we worked with the group that creates the official United Nations population forecasts that are widely used everywhere. They normally stop in 2100. We only needed 200 more years. That was all we needed for the social cost of carbon. And they were like, oh yeah, that's great, we can do that. And so they used the model that they have already, and then they convened an expert panel of demographers and came up with the population forecast. For the economic growth projections, we used a two-fold approach. So we recruited a group of fantastic time series econometricians, Mark Watson and Jim Stock from Harvard here, and they did a statistical long-run forecast of GDP. And then we constrained that with an expert elicitation exercise, because the vast majority of people in the economic growth literature thinks that if you just extrapolate current trends, you will get it quite wrong. And we got a really fantastic panel of people for that. And then for the emissions, we wanted to come up with a forecast of emissions that is most likely, right? That's a probability distribution. So we didn't, traditionally, these kinds of scenarios are business as usual scenarios or make certain assumptions about policy. We told our experts, just tell us what you think will happen. And we don't care whether you think it's because of policy or technological change. Just give us your best forecast of what happens. And that's what we got out of this panel here. All right, so those are the RFFSPs that underpin all of this work. And now I will speed run through this and talk really quickly about the climate models that we used. This is maybe the most boring aspect of this, although I know that I was invited by Noel, who is a climate scientist. But really what we did is we just looked around, what is state of the art, and then we used that. Okay? So we didn't really do, that seemed like a, yeah. So we used the FAIR climate model and the BRIC sea level rise model. They are both run-of-the-mill, as far as I can tell, central estimate sort of climate models, simple climate model emulators. They represent uncertainties really well, and they allow us to propagate the uncertainties that we have from the scenarios through these climate models, add the uncertainty from the climate models on top of it, and get sort of these probabilistic forecasts at the end. This is what our forecast is for temperature at the throughout the whole time horizon. Okay, so this is sort of takes all the uncertainties from the scenarios and from the climate model and maps that out. Okay, I'm just rushing through here. Damages. What did we do on damages? So this is the idea of we are trying to understand how the change in temperature affects human systems and human welfare. And we picked an approach that is sometimes called the enumerative approach, where you try to understand the impact in different sectors of the economy individually. There's another literature that just tries to statistically detect, the impact from temperatures on GDP, for example, without really understanding which parts of GDP might be affected here. And both of these approaches have pros and cons. The con approach from the enumerative approach that we used is certainly that it is incomplete. So whatever we enumerate is in, but then everything we didn't enumerate is not in. Okay, so that's sort of a problem. With something like a GDP approach, you catch throw a wider net, and you might catch things that you didn't even think about. But on the other hand, especially in this policymaking context, policymakers really like to understand what you're actually talking about, and there's enumerative approaches much more adept at that. So those are the 4 damage functions we had in our model. We estimated the impact on mortality. We estimated the impact on energy consumption. So this is actually a plus-minus thing. So we expect to use more energy if it gets warmer for air conditioning, but we also expect to use less energy for heating. There's an asymmetry here. Once you no longer have to heat, there's no additional benefit of warmer temperatures. Whereas with AC, as it gets warmer and warmer, there's an unbounded increase in energy that you use for that. So at the end, this is sort of a net harm. We looked at the impact on agricultural productivity. That has been the most studied sector of them all. And then we looked at coastal damages. So this is sea level rise and how that inundates land. And you might want to build protection, seawalls against that. And so that's sort of covered by the coastal damage module. There's a mix of methods involved in all of this. Some of this was meta studies. Some of it was based on more detailed integrated assessment models. Some of it was based on detailed process models here in the coastal damages. Some of it is more based on econometric type studies. So there's the spirit here is not we try to be consistent and sort of have a unified approach. The spirit is, what can we even do? Because this is really hard, and what's out there and what can we use? And that's sort of how we put this together. Yes? Yeah.
So this is the lower bound, like.
Yeah, so this is exactly what I meant with the problem of the enumerative approach. Those 4 things we capture. Anything else that climate change might do that you think is harmful, we don't capture. It's a 0 in our estimate. Now, if I'm a smartass, I could say it's unclear whether that's a lower bound or not, because some of these additional sectors could be benefits, right? It could be that something gets better if it gets warmer, but in practice, it's a lower bound, right? So I think we have sort of a rough sense of the types of things that are missing here, and most of them are harmful. Yeah. All right. I think I will skip all of these details here and talk about discounting. Okay, so you saw this equation before. So we have this table of marginal damages. We want to add it up. But before we add it up, we apply weights. Okay? So the marginal damages are a random variable. That's important. And the traditional way to apply this weight here is using a constant discount factor. And you can think of this as the weight gets smaller and smaller as time progresses. So you just give less weight to things in the future based on the distance and time. Okay? That's sort of what was used by EPA before we came in with this stuff. And we replaced this with a Ramsey-like consumption-based capital asset pricing based discounting story. And I'm going to try to give you an intuition for what that is. Okay? So the discount factor here uses this equation here. There are 2 parts in our new discount factor. One is a pure time discount factor. That's the same thing as we had before. It just discriminates against the future because it's in the future. And it's just the distance in time between the present and the future that determines that. I'm not going to go into the reasons why we do that. But then there's this part here. And that tries to discriminate against future harms based on the situation when that harm happens. Okay? So the idea is, if there is a dollar damage in one state of the world in 2050 where we are very rich, or the same dollar damage in a state of the world in the future where we are quite poor, we want to give less weight of the damage in the state of the world where we are rich, because that extra dollar harm is less harmful to us if we have more resources overall. Okay? So it picks up the correlation structure between your overall well-being and the marginal damages, and then adjusts discounting based on that. And so at that point, this one's also a random variable, and there are correlations between these 2 random variables because consumption in the future is uncertain. Okay.
So because you talk about some places rich, some time rich or poor, and then you are doing this global calculation, I assume. So how you consider different countries?
Yeah. So this, I'm going to defer this. This does not take into account income differences between different parts of the world. There's a long literature on equity weighting and the social cost of carbon that expands this logic to different regions. We published a paper in Science 2 years ago that takes all of this and shows the results for that. It makes a big difference, but I'm going to skip it beyond that. Yeah. But this discounting, this state contingent discounting really makes a big difference. So this is taking 10,000 runs from our model. In blue, we use a constant discount rate, so that does not discriminate against this. In black, we use the state contingent discounting. And on the x-axis, you see the time average growth rate. So essentially, larger growth rates means we're better off in the future. And on the y-axis, you see the SEC. And you can see that in the constant discounting rate, what happens is all the high SEC estimates that we get happen in states of the world where we grew like crazy. Okay? So that's fine. If we have high marginal damages, but we are 10 times richer than we expected, we can stomach that. Okay? So this is sort of the expected social cost of carbon of $500 is driven by the fact that there are high SEC estimates in some states of the world, but those are states of the world where we are very, very rich. Okay? And in our the discounting approach that we used, that gets corrected, okay? Because the discount factor is adjusted by these correlations, and so then we get an expected SEC of $180. All right. Results. What did we find? This is our main figure. If there's, I don't know whether any Julia folks are here. I think the team was really mad at me at the end because I insisted that I would do the plot in Julia Vega Lite package. And I think no one was happy about that. But I think it looks beautiful. OK, so this is our central result. It's a probability distribution of the social cost of carbon. The line is the expected value. So that's really what we care about for different discount rates. And the 2% discount rate is our central estimate here. You can see that there is a right tail for these estimates. Okay, so there's a larger downside risk that it might actually be higher. It's a skewed distribution than lower than our central estimate. And this is, yeah, we always did 10,000 Monte Carlo simulations from our model. And I think I can skip that. I'm going to skip this one as well. This shows you the breakdown between our 4 damage functions that I introduced to you. Okay, so I told you we really just have 4 damage functions. And so this is the total number here. And then we break it down into the 4 different damage functions. The most important one is health damages. So this is mortality impacts from climate change. There's a way in which economists value mortality impacts. For those of you, I don't know the fraction of economists here, so I'll give you a hint of how that works. We look at how people value small changes in mortality risks in other settings. So you might require a higher salary if you work in a coal mine because you think you might die a little earlier. And then we rescale that pricing of this mortality risk and adopt it for the increase in mortality risk that might be caused by climate change. That's sort of roughly the idea that we use here. And mortality is our biggest driver of our cost. The second one is agricultural damages on agricultural productivities. And then both energy and sea level rise are small numbers. Sea level rise always really surprises people. Why is that so small? And the reason it is so small is twofold. One is sea level rise is really slow. So things only happen after centuries. And then discounting really makes those numbers small. And then the other thing is it turns out sea level rise, there's an effective adaptation mechanism. If you have the resources, you build a seawall. That's not a complicated technology. And these models make really strong assumptions that these kinds of adaptation options are widely available. Maybe too optimistic, but that is sort of the explanation what happened here. OK, gonna skip this. We just did the same thing for social cost of methane and some other greenhouse gases. Yes. OK. I took out one slide, but I'm going to talk about it verbally now. Someone asked, like, what caused this large change from the $50 to the $185 between these 2 generations? And we did a pretty careful analysis of that. And I can tell you the major driver was that we changed the discounting scheme. So that was the biggest difference. There was also a little bit of an impact of our damage functions. So our damage functions are a little bit higher than the previous generation damage functions. But that was not the biggest reason for this change. The biggest reason for this change was that we adjusted the discounting scheme, and that explained the difference. So maybe it was another confirmation that economists are not wrong to fight about the discounting, because it is, at the end of the day, probably the knob that is the most important for the results here. Okay. Final thing I want to talk about is building computational tools in policymaking. I know that there's this was because of the Julia crowd. I don't know whether the Julia crowd is even here. It was actually a major part of this project. How do we build a tool that we can use for this kind of policy advising and and I want to talk a little bit about that. So I just want to start out by thinking about when we started this long project, what were our stakeholders? Who do we care about? Normally when academics write papers, we write it for the journal we submit it to and our close colleagues that we read, and it's like maybe a group of 5 people or something like that, right? And that's our audience, and when we build code or tools, as long as those 5 people can maybe read it, it's good enough, right? But we were in a very different setting here. So we really wanted to target 2 worlds here. One was researchers, and then we had this whole policy world. So that's me. That's sort of people that dedicate their lives to building integrated assessment models. So that was sort of one group we wanted to work with. But we wanted to change this so that it was not me building a demographic model anymore, right? So the first group we wanted to add in here is we wanted to collaborate with domain experts that know parts of this puzzle, but not everything. And we wanted to make it much, much easier for them to work on their stuff and not me being a bottleneck for incorporating that. So that was sort of the first group that was really important to us. The second was we wanted to work with EPA scientific staff. We didn't want to have a world where they hire us, they tell us we want an SEC, 2 years later we throw a number at them, okay? We wanted to, EPA has fantastic researchers that are technically incredibly good, and we wanted them to be in the loop for the whole thing and collaborate with them on this. And this came out of my, I had worked with them for 10 years before that, and I knew that that is the type of relationship they want. We wanted to make whatever we build accessible to researchers that use integrated assessment models. There are often people that say, hey, I have a different problem. I could use an integrated assessment model to explore something quickly. They don't want to spend their career building one, but they want to run it and change something or something like that. So we wanted to cater to that audience. We also wanted to cater to people that don't even want to do that, general climate economists. They can just use the SEC number. That has worked quite well. We knew that EPA scientific staff, for the publication at the end for the regulatory impact analysis, they have transparency requirements. Okay, so and EPA is was really committed to making everything they do transparent, so that stakeholders, the public, can understand it. That NGOs can go in there and run the model and see why is EPA coming up with a dollar figure of a certain kind. So we wanted to enable them and support them in that. And then in the back of the mind, that was the least important one. But we knew that maybe other EPAs in other countries might want to pick it up. There might be consulting companies that want to use it. And we wanted to sort of create something that caters to all of these people. Okay? So the idea of one long script that no one understands, that doesn't work with this kind of setup. And then I just had a lot of things that I've seen in my years my background is actually in software engineering before I started in economics. There was just a long list of things that I really wanted to do. I didn't want people emailing code back and forth because you will use the wrong version for the final run, I promise you. And also we were like 25 people, you can't do that. We also didn't want people emailing results back and forth because you will, again, use a version of the results where no one knows who ran that at what point, and you cannot trace back how that was actually generated. We didn't want to have slow code because in the policy world, there are actually deadlines that matter. There was a date, and if we weren't done, it would be a real problem. And EPA has often, there are a gazillion stakeholders in the federal government, and then someone has the idea, hey, what happens if you do that? And you need just really fast turnaround times, and you cannot say, it will take me 4 weeks. That's just not an option. So we needed something that is fast. We didn't want complicated code, because complicated code has lots of bugs, and this is a pet peeve of mine. I think there's studies how many bugs per lines of code a good programmer writes. I think most scientists are bad programmers, and so it's dismal, right? So it cannot be complicated. It makes it difficult for newcomers to come in. And then also the people at EPA don't have time to deal with complicated stuff. And then we didn't want to have it as closed source because I think that's ridiculous in this day and age for something that informs public policy. So we created this integrated modular framework, the MIMI computing platform. So this was sort of a computing platform where you can build in integrated assessment models where all of these things that I pointed out would not be a problem and where it would cater to all the stakeholders that I described. And the core idea here is that integrated assessment models you can really think of as Lego pieces that you put together. There's a Lego piece for the climate science. There's a Lego piece for the carbon cycle. There's a Lego piece for the health damage function. There's a Lego piece. And so we wanted to build something where you can put where these different Lego pieces can be built by different groups. And at the end, you can put it together. And you can easily swap something out. Hey, I want to run this model with a different climate model. It should be as easy as switching out a Lego piece. So that was sort of the core philosophy of this. We wrote the whole thing in Julia, because I said we will write it in Julia. And it was actually a really good choice for this kind of exercise. And I just want to sort of show you something. Essentially what we did is we went with something in the computer science literature is called an embedded domain-specific language. So some of you might have worked with domain-specific languages. So for example, GAMS, I would put Stata into that category, are programming languages that were created for a specific niche audience, for a specific purpose. And they were great for a long time, but they also have a problem in that now you don't have access to like normal packages and things like that, okay? And so embedded domain-specific languages is the idea that you take a general-purpose programming language, and then you embed a domain-specific syntax in it. So you have the best of both worlds. And I just want to show you how this looks for Julia. So this is the definition of a simple component, for example. It's one of the damage functions. And so you have parts that are just normal Julia code. Like here, the function, the runtime step function. It's not complicated, a few lines of code. And then we have other parts that are this embedded domain-specific language where we provide a framework how you can specify the structure of this component. And so we fused sort of these general Julia programming languages with a domain-specific part to create something where you can express components in a really succinct and small and minimal form, which makes it much, it's easy to find where the equation is here, right? You don't have to hunt through 200 lines of C++ code that has 180 lines of code that do something that with memory management or something, So that was the goal here. We utilized the Julia package manager for distributed workflows. So the different components essentially become packages, and then you put them together. And then because we also created this platform, it allowed us to provide centralized things like uncertainty analysis, sensitivity analysis, optimization, and visualization tools that work on these sort of final models that are really useful. It's been a big success. So these are all the integrated assessment models that are now running on this MIMI platform. And so a few of those, do I even have? OK, I didn't even put the one that we built on here. That's pretty silly. But lots of other groups sort of picked this up and built individual components. And I lost track at this point who is using it, which I think is always the sign of success for an open source project if you no longer know your user base because it's too large. All right, policy uptake really quickly. EPA used this framework. It worked really well, the collaboration between the different groups. EPA has then started to use it for other things as well because it was sort of convenient. Germany and Switzerland used it for their SCC estimates. And I think this goal of having, I continually run into people that ran the GIV model and they say, yeah, it was pretty easy. I didn't have to dedicate a career to get my feet into this. So what lessons did we learn here? It's a delicate balance to cater to all of these stakeholders. I think experience matters a lot if you try to build something like this. I had 2 previous attempts at building something like that were horrible and didn't work. And I had about a decade of time of working with EPA. So I just knew my audience really, really, really well at that point. And I think without that, I would not have. I think that would have gone in a different way. And then you just need to have a team where the CS part and the scientific part and the policy parts are equally on equal footing, right? This will not work if a group of brilliant economists hire a research staff programmer. You need someone who actually is really dedicated to this and approaches this from a CS type view. All right, this is the URL. If you want to use it, you can because it's all free. All right. This is what I promised you I would skip. So let's just go to my conclusions. Yeah, so we built a new SEC tool for the US regulatory process. It started a lot of exciting research that I now skipped over really quickly, but we did things about equity, discounting, robust decision making. I think this is really fun because it has a potential to bring researchers from so many disciplines together. Sometimes, interdisciplinary research sometimes has sort of a, I don't know, it's sometimes hard to pull off, but this is a great unifying tool. We've had demographers, economists, impact people. It's awesome. And then because it is sort of high profile, it has really attracted a lot of interest from policymakers and decision makers. So another nice thing about this space is that you are not in an ivory tower. Your work will actually be picked up. And that's it. I hope you learned a little bit about social cost of carbon. Thank you.
Hi, thank you very much for the talk. I just kind of going back to the first part. I think you mentioned that you built this model and you built in analysis for covariance between the different models. Is that right? So I'm just curious how you were able to do that, given a modular design, how you would propagate the covariance from one model into the other parts and end up with it.
Okay, so where we did this was with the scenarios, with these three, population, economic growth, and emissions uncertainty. The way, and it was the correlation between the economic growth part and the emissions part where we really got the covariance thing right. And the way we did it is that we did conditional elicitations of our experts for the emissions. So remember, the emissions was an expert elicitation, so we went out, I think, to 10 people that are experts in emission forecasting, and we didn't ask them what is your what do you think the emissions will be unconditionally. We told them, if economic growth is this, what do you think? What are your percentiles for emission forecasts? And then and so those components are actually coupled, right? So there's actually one component for the RFFSP in our module that spits out the combined population, economic growth, and emissions things just exactly for the reason that you mentioned, because they need to be correlated. There are no correlations between any of the other components on the input side. Of course, there are lots of correlations emerge on the output side, but that is sort of an emergent property of these models. Yeah, I don't know. Does that?
Yeah, thank you. I'm interested in what kind of workflow was for deciding what modifications you would make to how the discount rate was determined, and if your team considered anything beyond the modification you did make, considering future wealth, maybe something like a time variable discount rate. Yeah.
Okay, so the discounting, I left out a lot of things, but at the end of the Obama administration commissioned a report from the National Academies of Sciences on what the next steps in the social cost of carbon world should be. Also, by the way, great way to do this, to just go to an independent scientific body and ask for, hey, what should we do, right? That was a good, from a policy design point of view, a good thing. And that report from the National Academies of Sciences came up with this specific recommendation for the discounting that we then implemented. So in our project, we didn't really explore alternative options for the discounting. We just went with these National Academies recommendations. I've written many papers about different discounting exercises. I'm writing another one right now because the discounting is just really hard, and even small changes make a big difference. I think I maybe leave it there because it gets very nitty-gritty. If you have a few minutes afterwards, I'm happy to chat. But yeah, it's very much in the weeds, sort of the differences there.
And I think with that, maybe we'll wrap up the formal program, but it sounds like folks could ask you questions afterwards. So thanks to our speaker again.
Thank you.